This paper addresses a critical challenge in medical AI. While large language models perform well on structured medical tests, they falter when answering open-ended questions that patients might ask. The authors identified two key problems: hallucinations, where models generate factually incorrect information, and incomplete responses, missing critical aspects of diagnosis, treatment, or prevention. Rather than pursuing expensive fine-tuning approaches, they developed a structured reasoning framework that mimics how medical professionals approach diagnostic reasoning without requiring additional training.
Figure 1 visualizes the cognitive architecture behind MedSocot. It illustrates how professional medical reasoning unfolds in a structured sequence. When a doctor encounters a patient question like, "What is the relationship between Noonan syndrome and polycystic renal disease?" they don't immediately generate an answer. Instead, they move through distinct cognitive steps: understanding the question, recalling relevant medical facts, analyzing implications, considering impacts, checking reliable sources, and suggesting next steps. This structured approach ensures comprehensive and accurate responses while minimizing errors. Section 3 details the methodology behind MedSocot. The authors developed their approach based on established clinical reasoning theories, breaking down the diagnostic process into 7 systematic steps. This structured framework provides LLMs with a clear reasoning pathway that mirrors human cognition. For implementation, they designed specialized prompts that guide models through each cognitive step. For models with limited context lengths, they developed stepwise reasoning methods. Their optimization strategies include one-shot examples for validation and specialized markers to extract important content. Figure 5 demonstrates MedSocot in action for a query about Lexapro, escitalopram. The visualization shows how the model breaks down its response into distinct cognitive components, each addressing different aspects of the medication. Rather than generating a single block of text that might miss key information, the structured approach ensures coverage of mechanism of action, clinical uses, potential interactions, and follow-up recommendations. This systematic decomposition helps the model organize its knowledge effectively, resulting in more complete and accurate responses. The experimental results in Section 4 demonstrate the effectiveness of MedSocot across multiple models and datasets. When compared against state-of-the-art methods like OLAF, which requires fine-tuning, MedSocot achieved superior factuality scores without any additional training. Remarkably, these improvements transferred to smaller models, with LLama 3.13b Instruct achieving a factuality score of 84.5 using MedSocot. The approach showed particular strength in handling complex health search queries and medication questions, where precision and comprehensiveness are especially important. Table 1 provides a comprehensive comparison across different models and approaches. The data reveals that MedSocot consistently outperforms both zero-shot baselines and the fine-tuned OLAF method across all tested models. For example, Mistral 7b improved from a factuality score of 59.1, zero-shot, to 79.3 with MedSocot. Notably, the approach benefits both general-purpose models like LLama 2 and medically fine-tuned models like BioMistral 7b, suggesting that structured reasoning complements domain-specific training. The table also shows improvements in words composition metrics, indicating enhanced coherence. This research demonstrates how structured outputs can dramatically improve LLM performance in specialized domains without expensive fine-tuning. By guiding models through a systematic reasoning process, MedSocot achieved state-of-the-art results on medical question-answering tasks. The approach's effectiveness on smaller models suggests it can help democratize access to high-quality medical AI. While the current implementation focuses on medicine, the underlying principles could extend to other domains requiring expertise and precision, such as legal documentation or technical support. This represents a promising direction for enhancing LLM capabilities through better reasoning frameworks.